today's TAMIDS talk. So Johan is an assistant professor at Stanford University, where he's in the Department of Management, Science, and Engineering. In his research, he develops algorithmic and statistical frameworks for analyzing social networks, social systems, and other large-scale social and behavioral data. And so this includes a lot of work at the intersection of probability and machine learning and social network analysis and a lot of other cool stuff. So prior to Stanford, he was a postdoc at Microsoft Research in Redmond. And he obtained his PhD working with John Kleiberg at Cornell University in applied mathematics, during which time he also held an affiliation with Facebook data science. So he has a lot of different awards. Among other accolades, he's got a Young Investigator Award from the ARO and several Best Paper Awards, including a very recent Best Paper Award from ICWSM, as well as the 2016 Eugene L. Grant Undergraduate Teaching Award from the department at Stanford. And in addition to all of the accolades, I happen to know he gives phenomenal talks. And so you are all in for a treat today. He's going to be telling us about some work he's done in discrete choice theory. So turning it over to you, Johan.
Thank you, Nate. I'm also a big fan of expectations management. So we'll see if I can live up to the high bar that you just set. Thank you for this invitation. It's a shame to not, when I got the invitation to A&M, I was like, oh, I haven't been to A&M, it'd be lovely to visit. I was in a one-on-one earlier, I was saying I've been to Austin, Houston, San Antonio, Dallas, and there's sort of like a circling in that one of these days I'll make it to College Station. So until that day, it's very nice to join you virtually. My talk today is going to be about a subfield of what could be called machine learning or applied math or mathematical modeling, about preference learning. So the general area of sort of understanding good models and the evaluation of good models of human choices, human ranking, sort of decision making in various primarily online contexts, where this is sort of a problem that the mathematical psychology people were modeling back in the 20s, but very actively in the 80s and 90s. And then as behavior moved online and became highly instrumented, there's sort of been a lot of interest in this area from the more computational crowd who deals with very large data sets. It'll include work from two former PhD students, Stephen Reagan and Arjun Seshadri. Stephen now at Twitter, Arjun now at Amazon. These are sort of students who worked in this area, and then it turned out that industry was very attracted to their skills. Alex Basikovich is a sort of longtime on and off collaborator, behavioral economist at Facebook AI Research in New York Fair, who has provided a lot of sort of the behavioral econ anchoring for a lot of these ideas. So the setting for a lot of the work that I'm talking about today is this idea that people have preferences over sets. So I mentioned that the psychologists were studying this as far back as the 20s. The study of sort of how people make choices from sets became very hot in the 1970s. So McFadden over at Berkeley was in the 1970s starting to build out the language of discrete choice for modeling transportation decisions. So what is your utility for a bike ride versus a train ride versus a drive? Famously, it was sort of like part of the evaluation of the development of the Bay Area Rapid Transit System, the BART system, which everyone says like, oh, that is not a good selling point for discrete choice because BART is highly dysfunctional if you've traveled around on the trains in the Bay. And then Mansky, also in the 70s, was looking at how students were making choices of whether to go to college and where to go to college. And then this modern context is sort of looking at usually digital slates. So you have a couple of news stories that are shown to a user. Which one are they going to choose? A couple of ads being shown. Which one are they going to choose? And then the broad area of sort of recommender systems. When you're browsing Netflix, you can think of the modeling of human choice when interacting with the recommender system as essentially a preference learning task. There's a lot of variations on these problems. There's the sort of all the fancy ways in which you want to be doing online learning. There's sort of time varying preferences, all those things. We're mostly going to focus on the basic problem, which is bulleted out below here. So you have there's a universe of alternatives X, and which is sort of like all the possible things. and then we're going to show somebody a choice set, C, which is a subset of X. And the question is, what are you going to choose? And we're going to try and model that probabilistically. In the discrete choice setting, we're going to look at learning distributions over items for all sets C. And this is a pretty particular object that we're going to study, which is sort of like how people make choices over all the different subsets of a space, of a discrete space. And then ranking is the question of putting distributions over permutations or rankings. Usually you're mostly interested in sort of like good distributions over the top K few items, but in general, the problem is one of sort of having data where people have ranked things and asking like, what's a good descriptive distribution that can be learned from data that sort of captures the distributional properties of an empirical distribution. There's going to be a fundamental object of study here, which is sort of the idea of a choice system, which is this overlap of how you're making choices from all the overlapping sets. We're going to talk through what that is. Then we're going to talk through the workhorse assumption behind discrete choice since the 20s, very actively since the 70s, which is a mouthful assumption. It's the assumption of the independence of irrelevant alternatives. It's this idea that your choices are not dependent on what's on offer, of the things you didn't choose. So an irrelevant alternative is something that was offered to you and wasn't chosen. And the basic assumption that drives a lot of the modeling in discrete choice is that your probability of choosing something doesn't depend on what else was in the set. And what this talk is going to be about is about choice models that move beyond this assumption, because this assumption isn't always so valid. So we're going to talk about choice models that move beyond this, and then ranking models that move beyond this. And this is a sort of a wrapper around two papers that were in the last 2 years that were at ICML and then NeurIPS just last December. And then time allowing, I will try and bait you with a more theoretical question, which is how do you test whether data obeys this assumption as a sort of hypothesis testing, or really it's becomes a very combinatorial question. So it has a lot of the flavor of a property testing problem in theoretical computer science, asking whether or not a choice system is situated within a specific subspace of all possible choice systems. Okay, so that's our agenda. So now I want to first introduce you to this fun object that is a choice system. So it's not, if you haven't seen a choice system before, it's not every day you get to meet a new space, a new thing. When we think about sort of mathematical objects, we have our classic sort of vector spaces like Rn, which is sort of like an n-dimensional space of reals. We have our n-dimensional simplices. We have the space of permutations that will come up here, sort of the symmetric group. There's a lot of these are sort of relatively vanilla vector spaces, maybe like the space of polynomials, or sort of binary matrices. These are all different spaces, and they admit their own algorithms. Their data has certain structure. The thing one that we're going to be talking about today is this idea of a choice system, which is the following multifaceted object. So what we're going to do is we're going to say there's a distribution, the probability of choosing X from C, for every C for every X. Right? So for every set that's a subset of a space, this is sort of the main collection object. For every set that's in a space, we're going to place a little distribution over the items in that set. And so it's sort of, if there's 5 things, it's all the little distributions over the pairs and the triplets and the quadlets. And that's the object that we're going to try and learn. And what's really the angles of attack on modeling this object is about what assumptions you're willing to make that relate distributions across different sets, right? So like if you have a specific set of 10 things, you add 1 thing to it, did all the observations you made on the set of 10 things, is that transferable to any analysis of choices over the same set with just 1 other thing added? Like it probably shouldn't change things too much, right? Like it's basically the same menu, you just added 1 more thing. your willingness to make those types of assumptions is really your doorway into sort of like doing modeling in this space versus like being unwilling to make any assumptions. You're kind of viewing every set as its own little categorical distribution. One thing that we're not going to talk about that's a different sort of a thing two relative our thing one is this with what probability we see different sets. This is a subtlety that's important if you want to dive into the literature on these questions and the theory of them. But in general, there's sort of this other distribution, which is the probability with which you see different sets. Right? That actually like doesn't matter to us. We're only going to be handed sets. It's sort of a conditional problem. We're conditioning on the set that's in front of us, and then we're trying to model the distribution of choices inside there. And it features, there's this literature in the sort of details of what's the object. You have to think carefully about this. And it's sort of a classic source of confusion, or if you're not aware of this, you can try and align results and have some difficulty. But in general, we're just going to focus on the conditional probability of every possible set. Okay, so this is a very important object. It's not that commonly seen, so I just want to introduce it slowly, and then we're going to pick up speed. So consider this little set here, ABC. There's three possible things that you might want. Well, what are the possible subsets? Well, there's the subset AB. There's the subset AC. There's the subset BC. And then there's the full set itself, ABC. Right? So there's a question that came in here as I just sort of enumerated all the subsets that are non-trivial, I should say. I'm not doing the subsets of size one. There's a question that came in. The C equal 2 exhibits special properties compared to other sizes of C. Great question. The literature, when all the sets are of size 2, you're basically acquiring a bunch of pairwise comparisons data, right? So this is a really popular domain because it comes up in a lot of sort of competition modeling in things like sports, sort of trying to figure out the qualities of different teams or tennis players, et cetera. And then you have a bunch of pairwise comparisons data. The really nice thing about pairwise data is you can kind of think of it as this graph of like X beat Y, Z beat X, and you get this sort of like directed graph, and a lot of the analysis of that type of data has a language of analyzing directed graphs. But in general, it's sort of a special case of the analysis you can do on arbitrary sets. I'll try and make some pointers to sort of like if all your sets are only of size 2, a bunch of this gets a lot simpler, and it might even reduce the sort of known results, but it's a good question. We're sort of working in a generalization of pairwise preferences, which is the special case for all sets of size 2. So let's do here, we have this simple set, and there's 4 possible different distributions. And, we really just have like a little histogram for every set, where that's your A, B set. If you're comparing A and C, maybe A is more popular compared to C. And then you're comparing B and C, and maybe they're actually even. And then if I ask you to choose between A, B, and C, whoa, A actually looks really good, right? Something like that. There's just totally arbitrary different little histograms over the items in every possible little subset. One fun thing that I haven't seen done before, and an object that I find useful for, or a visualization that I find useful for thinking about this object, is saying, consider the following drawing where you put the items at the corners of a simplex, and you say, well, along this little edge here between A and B, we're going to put a black dot sort of proportional to sort of the probability of picking B over A. Along the next edge, we're going to look at A versus C and say, okay, it's mostly about picking A, and then B and C were in the middle. And so these are sort of like the probability distribution on the sub-simplices of just size 2 sets. And then if you were trying to make a choice from the full set, you're now on the actual face of the simplex. So that's sort of like you're more likely to pick A versus any of the BCs. So there's sort of like on the triplet, there's this point in here, which is closer to A, and then splitting B and C. And then you can ask this question of modeling, like, are supersets related to subsets? is about asking, like, is the distribution, or is the point on the face of the simplex related at all or constrained by the ways that the subsets behave? Or are the subsets somehow like a projection of what's on the face? I'm not going to develop that so much here, but it's something that I haven't seen in literature, and I think it's like a useful way to think about all these overlapping sets as sort of like living on subsimplices, subfaces of like some general object, and it somehow the ways that the edges overlap is useful for me in my mind. The next slide is my backup slide in case my iPad didn't work. So I'll just skip that. Okay, so that's the type of thing that we're going to talk about today. This object that has sort of preferences over different subsets. And in the absence of assumptions, you get something that McFadden called the universal logit. It makes no assumptions about the relationship between the different distributions on different sets. You're on your own, no matter for every set that you're handed. So Luce, working in the 50s, more in the math psychology literature, goes ahead and says, well, like having a different distribution on every set, that's a huge nuisance. It seems both impractical and implausible. So we're going to make here's a really strong assumption. Let's assume that whenever there's two items in a set, X and Y, we're going to say the ratio with which you pick X to which you pick Y is going to be independent of what else is in the set. So that left-hand ratio, which is the probability of picking X from XY compared to the probability of picking Y from XY, that's going to be, it's 10 to 1 or something like that. We're going to say that if you add a bunch of things into this sort of like additional set C, you add a bunch of things into the set, the ratio of X and Y isn't going to change. And that's the sort of mathematical formulation of the independence of irrelevant alternatives. C are these things that are the irrelevant alternatives. And axiomatically, if you make this assumption, you get that all of the probabilities sort of admit what's called a ratio representation. The probability of picking an item is proportional to some like latent quality. The probability of picking X is proportional to some latent quality. You can see that if you take this type of expression down here and you plug it in either on the sort of like the left-hand side or the right-hand side, you see that the denominators are going to cancel. The denominator of the bottom thing is going to cancel, and you're just going to be left with this like gamma X over gamma Y on both the left and the right. And that's sort of like, that's not at all a proof, but Luce in the 1950s is doing axiomatic discrete choice and sort of notices that this assumption as a necessary consequence, you get this like very simple representation. Now, if you've never seen these choice stuff before, you've probably seen the multinomial logit functional form, or the softmax, as the machine learners like to call it, where if you basically rewrite these latent qualities as inside an exponential, you get that the probability of picking an item is sort of a softmax, an exponential over a sum of exponential, of some like latent utility, which is a utility space, is what the economists like to work in also. And this is the idea that items have latent qualities and they're picked proportional to the exponential of these qualities is kind of the canonical writing of the multinomial logit model, the MNL model. And it's this major workhorse of modern machine learning, including like anything in discrete outcome spaces. You're basically working under these like softmax functional forms. If the utilities are linear functions, so if you have these, the utility of X is some sort of feature vector times a beta parameter vector, that's a linear model. And there's a hashtag IJALM, which stands for It's Just a Linear Model, which is this Twitter hashtag where you can go look up some of the debates about how people like to put window dressing on things that are really just linear models. I think it was coined by Danielle Witten up at UW in the stats department there, where she was sort of saying that many things that people think are complicated, they're actually not that complicated. They're just linear models once you set the link function, and generalized linear models, and the things that are taught in introductory graduate statistics. So that's the assumptions people are going to make. I've got the obligatory robot slide. So is this a reasonable assumption, or does this assumption deliver? So it's, first of all, it hugely simplifies the any data learning problem, because you're just saying that it's just about the sort of every time an item shows up, no matter the set, you can assume that it's like providing coherent, translatable data about an item, because all the other items don't say anything. It's just about you kind of trying to learn the latent strength of an item. So is it a valid assumption? So there's this, in the discrete choice literature, there's this famous book review that De Breu does in 1960 of Luce's monograph. So this is like the history of the field. De Breu was an economist, microeconomist, or actually micro-macro, went on to win an Econ Nobel for his macro work. But he's reviewing this book by Luce, and he says, oh, well, this is like very highbrow example where he says, well, I don't believe this assumption, because consider comparing the following two choices. In the one choice, you're choosing between a recording of Debussy and a recording of Beethoven, versus another choice set, you're choosing between Debussy and two different recordings of Beethoven. And it's quite natural that in the triplet, you would sort of like distribute your probability mass of wanting Beethoven across the two Beethovens. And like your probability of picking Debussy should be the same in both of them. So they should be the same absolutely, not the same in ratio. And so I don't buy this assumption. So the story goes that this sort of example went above the heads of most readers. And it was only in the 1970s that Daniel McFadden was rehashing some of this basic choice stuff as he was applying it in econometric settings. And he said, well, imagine that there's a red bus and a blue bus, but actually like on one day there's two red buses. Do your preferences really change over the fact that there's two red buses? And everyone's like, oh, that makes sense. That's like way more attractable than like Debussy recordings, partially because it's like, how do you pronounce Debussy? And so that the red bus, blue bus is like now the canonical example. So modern examples, there's a literature that goes back at least to these 2012, 2014 papers observing that the click-through rates on ads depend on not just on the ad itself, but what it's shown in the company of. So these are sometimes called group effects, which is sort of what's documented, or preference reversals is the first paper there by Young, Mishra, and Chappet. Basically observing that there's not just this universal thing of like ad quality. There's sort of like certain ads, when they're shown, raise the tide for all click-through rates, because they're maybe like visually attractive. Maybe it's a photo one, and they attract the eye to the sidebar, and then it like everything gets clicked on more or clicked on less because it's offensive. And so there's really interesting like auction design questions, if that's your cup of tea, about sort of like, oh, how do you price in that externality, because it's basically an externality. But these auction problems are hard. Almost all ad auction pricing type of settings just assume there's an inherent ad quality, and that's like hard enough because of the way that ad auctions have to be super fast, et cetera. Austin Benson, in his as part of his PhD thesis, had this nice paper with Google folks. It's called "On the Relevance of Irrelevant Alternatives," documenting how in large-scale web browsing, IAA broadly doesn't hold when you look at how people pick which song to listen to from a menu, or which restaurant to go to when browsing Google Maps. This was with Google folks, Ravi Kumar and Andrew Tompkins, using Google data. You have these preferences that are sort of like nested, or some deviation from like clean IIA formulation, where your preferences exist over Italian and Japanese, and then within that, traditional Japanese and sushi, which is a so-called nested model. So particularly in a lot of these online settings, we now have huge data sets, and we're now seeing that like actually we could do better if we had a good model of choice beyond IIA. So how are we going to do that? How are we going to move beyond IIA? I'm now going to go through three different approaches, where I'm going to try and mostly sell you on the last of the three, and which are sort of like, they're all three different generalizations of an IA model in different directions. One's going to be based on, which is a standard version, which is sort of like changing a random utility model. The next one is builds off of a line of work in 2015 about sort of Markov chain models of choice, or Markov chain interpretations of the MNL model. And then the third one is, this was the main object of study in this ICML 2019 paper, and that's sort of what I'm going to focus on. Are there any, I've been sort of like keeping a high tempo. I should take a step back, breathe a little bit. Zoom lecturing is what it is. I would sort of ask, are there any questions at this point about sort of like this assumption or these contexts, when IA is reasonable, or like, you know, when I browse Netflix, I don't think this happens. Any stories anybody have? Just create some breathing room. Anybody? Okay, so if you believe me that your behavior is, that you are a subtle human, that your behavior is not just sort of very simplistic, you're going to want to try and understand how we can move beyond IA. There's also, I should add, traditional literature on mixtures and nested models that I'm not going to talk about today that are sort of orthogonal to this. You can mix these models as well. So here is one interpretation of what an IA model is doing. When you're picking items proportional to some like inherent quality, you're really saying that every item has a random utility associated with it, some random variable, xi, which is a mean plus a noise term. And the probability of picking an item is the probability that it's the max in joint realization of all the random variables. So you have these sort of like bumps on the real line, and your probability of picking purple is the probability that it is the max in a joint realization of a bunch of independent random variables. What I drew there are approximately Gaussians. If you let them actually be Gaussians, you have what's commonly referred to as a probit model. Not really going to talk about that much. If you let the distributions be zero mean Gumbel distributions or double exponential extreme value distributions, a rose by any other name smells just as sweet. If you let all those noise terms be Gumbel, then you get that the functional form of the probability of max has this ratio representation that we've seen before. So if these x's up here are Gumbel, the probability of any max has this functional form. And that's this like beautiful thing that if you've never done, if you sit down and do the half-hour manipulation with the Gumbel distribution, you see this once, you've sort of seen it, and you will see into the depths of this question. There's a lot of, even in the last 5 years, there's a lot of modern machine learning with softmax functions that uses sort of the Gumbel trick and properties of the Gumbel distribution. So if you want motivation for why you should sort of like do a couple of basic manipulations with the Gumbel distribution and see how this math works out, it's the driver behind this. If you do a Google Scholar search for a Gumbel trick, you'll see a bunch of like machine learning literature where you can do subsetting and sort of efficient negative sampling because of assumptions about the Gumbel distribution. So if you don't go for the Gumbel, you have this like broader distribution of like slightly different choice models that aren't assuming IA. So only when you have a Gumbel are you getting IA. And there's a huge literature that goes back to Feldman's characterization theorem, if you like sort of like more mathy things, of like what can a random utility model do. The interesting thing about random utility models is they need not be stochastically transitive. You can have weird like rock, paper, scissors type things, even with these independent random utility models. If you don't believe me, look up something called non-transitive dice. I'm not going to give an example in the talk, but non-transitive dice are this parlor trick that is really a random utility model in disguise. Work by PhD student Rahul Mukhijani was studying these random utility models and was able to make this equivalence between the stochastic transitivity and the concavity of the log likelihood function, or the convexity of the negative log likelihood of a certain style of parameterization. So sort of, there's a certain sense that with random utility models, non-transitivity implies optimization hardness. Now, convexity does not equal optimization easiness / hardness. It's not the exact boundary, but roughly speaking, you have a much messier problem on your hand if you are trying to deal with transitivity in random utility models, or non-transitivity random utility models. This is a slide for the Markov chainers in the crowd. I'm somebody who really likes Markov chains. This was a paper that was in Stephen Reagan's PhD thesis, appeared at NeurIPS in 2016. So here's one way to model a bunch of distributions over sets. Consider a Markov chain with a continuous time Markov chain for reasons that I could go into. Consider a continuous time Markov chain over a set, and you've got some rate matrix Q, and it's sort of like you're picking a digital camera, like, oh, there's all these like, and imagine that you're a darting eye that's like jumping between these different digital cameras, then you press stop, and that's like the item that you pick. So what you're looking at there is the stationary distribution over that set of the continuous time Markov chain with the rate matrix. And you can take that Markov chain and subset it on different sets. Just take the rate matrix and take like the sub matrix that's induced by a subset, and you get a different stationary distribution on a different set. So this, this collection of Markov chains that's defined by a single rate matrix Q is a really natural way to put a distribution on every subset in a coupled way, right? You have this like rate matrix that's there to like, oh, everything's just like oh yeah, you're just pulling out those sub indices and readjusting the diagonal. This style of choice model has a lot of interesting properties. It's not, the learning problem is not convex. It's not a happy optimization problem. But the idea for this paper stems from a really nice paper in 2015 by Meister and Gross-Glauser, part of Lucas Meister's thesis. He's now on the recommendations team at Spotify, which found that, which observed that there was a Markov chain interpretation of the multinomial logit. So it said that multinomial logit is the special case of a continuous time Markov chain of a particular way to parameterize the rate matrix. And so what we did in 2016 was we said, okay, beautiful. It also admits like a spectral algorithm for the multinomial logit problem because Markov chains often have spectral algorithms. What we said was, great, let's not do that special parameterization and let's look at the more broader choice model that we have. And so I really like that 2015 paper, and I'm fond of my own work, the 2016 paper. So that's another way to sort of like not do MNL using Markov chains, but optimization is a mess. Okay, so now I'm going to give you the third way, which is the one I said I was going to sell you on. So what we're going to do here is we're going to take a step back. Rather than starting from the multinomial logit, we're going to start from that. I mentioned that there's this arbitrary way to model choice. You just say there's a different probability distribution over every set, and it's just, they're all arbitrary. And so define these like the utility of an item in a set, like U of X bar C, as just a bunch of quantities. And you need to do some like degree of freedom constraining so that you say, okay, actually over all the items in a set, they sum to 0, but that's not that important. And let's just say that the probability of picking an item in a set is, a soft max of that utility. This is a universal logit model. It is an arbitrary model. You're putting a little separated histogram for every C on every item on every set. So there's this observation by Batzel and Polking, who are marketers, who did this really nice work in the 1980s, well out ahead of a lot of other people. And actually, I will argue that they were the ones who maybe invented all the TVEC embedding literature with this work, but that's a strong statement. There's other things going on in the TVEC literature, but what you're going to see is going to point forward to the TVEC machine learning embedding literature. You say, okay, consider that arbitrary thing, the utility of an item in a set. Do this like Taylor expansion like thing. So say, well, I want to describe that utility by first, this like first order, like, oh, the utility of the item, call that B. And then I'm going to say the utility of an item, sort of linear, sort of the conditional, like the effect of every Y on every X, and then like linear in all the items in the set. So when you're looking over at this utility of an item in a set, it's like first, it's the utility of the item. Then it's like the one-on-one effect of every item in the set. Next, do the two-on-one effect of every like pair of things in the set. That could like how every two things affect everything. And keep going. And it turns out that this is a like unique there's a unique expansion if you do your constraints properly. There's sort of like, it's just like a sort of like a Taylor expansion of a function in polynomial basis. You're doing like an expansion of the item level, pairwise level, triplet level, etc. And so what Batzel and Polking noted is that you can sort of say, oh, okay, like you have this universal logit. Let's just cancel everything that's really high order. And that's a huge mess. And let's just look at sort of this truncation and say, let's just look at utilities of items and sets as the item, and then like the pairwise effects of items on items. And overall, you get this like clean nesting of like item, there's like the basic model, the second order model of pairs, the third order model of triplets. And what they show in part of that work is that the first order model is MNL. All you're saying is that items have utilities that are independent of the set. And then what we're going to look at, and then they also note that the final thing is the universal logit. That was like a heavy lifting thing that they showed. But the interesting thing is to focus on things like this second thing, where you're just saying that things have pairwise effects on each other. So if you take that way of looking at items being chosen from sets, you can rearrange some terms, and you're basically saying that the probability of picking an item from a set is linear in these pairwise interactions, right? It's like the utility of an item X is like, it's about like the sum of the effects, the pushes and pulls of all the Z's in the set, sum over Z's in the set. And you could call this, rather than calling it an independence of irrelevant alternatives, it's a pairwise linear dependence, right? It's like pairwise, like just a linear effect, and it's only pairwise. The three-way things, higher order stuff, we truncated that away. And notice that we basically have this parameter matrix U that's sort of like n squared parameters, and we're convex in that. And we like convex optimization. I do, at least. And so this is actually like a really tractable model. You can make it low rank if you want to. So you take that U and you factorize it C dot T. And C and T are sort of skinny and tall. They're skinny matrices, sort of like a factorization, the rank R factorization. And you basically now have this like matrix factorization loss that's non-convex, but not that bad, because modern machine learners put that in the category of things that are not that bad. SGD does well. So what we were able to show was that what Batzel and Polking were doing in the 80s, they were doing nice theory, bad data. I don't know. I want to only give them compliments. I don't want to say anything unkind, but they sort of like worked out the stuff about the universal logit and the expansion. And then they sort of did some odd kind of quaint least square thing. It was clever for the time, but modern convex optimization theory wasn't in place. So what we were able to show is that, hey, actually this model, the MLE, you can put a upper bound on the expected risk of the MLE sort of like converging in on the true parameters. So if your data is actually generated from this model, you have this upper bound that is, M is the number of data points. So as M goes up, the upper bound's coming down, and the MLE is going to U star, which is the sort of like true U matrix that the data is generated by. So you have a upper bound on how far the MLE ever is from the true parameters, assuming the data comes from the model. But there's some really interesting things here on the right-hand side. There's a second eigenvalue of a Laplacian-like object. And so this is what's called structure-dependent convergence rates, because there are sort of things about the structure of how things are being compared end up bounding how quickly you converge. So it matters like how things were compared, both in a pairwise way or in a set way. And the first work I've seen on this, sort of a lot of it pulls up work that was in Nihar Shah's thesis, who's now at CMU, who used to did his thesis at Berkeley. That's like the main thing going on here, that you have sort of like a well-converging MLE for this type of model of choice beyond pairwise comparisons. And this is pointers for people in the crowd who know the following words. But basically, this is a Word-to-Vec type model. This is a CBAO type model. And so it's really also a convergence rate for CBAO, Word-to-Vec type models. And there's some other details there about negative sampling that I do know how to handle, but I won't go into. The convergence result is based on sort of a bunch of convex optimization M estimator properties for the full rank case. The bound still applies in the low rank case. It's just probably faster. It's a loose bound. There's been fun work extending this. There's sort of salient features. Laura Bolzano up at UMich and her student promoting a particular choice. So this was Kieran Tomlinson and Austin Benson's paper in 2020. Kieran and Austin had a really nice paper at KDD this year that's basically taking this embedding model and featureizing it, and they call it the LCL model. That's a great paper. There's sort of like a new breath of air coming into the choice literature, which you could say is like, oh, it's a TVEC for choice, but actually it goes back to the marking literature in the 80s, this like Batzel and Polking idea. So I want to give credit where credit's due. This is a not super interesting, because it's the small data that academics have, example of sort of like, oh, if you just have a logit model, you have sort of this high negative log likelihood. If you do a mixture model of a certain size, your negative log likelihood goes down. And then if you do this contextual sort of like pairwise modeling, you get lower negative log likelihood on 2 different data sets that are commonly studied. I don't want to belabor this too much. I can give you more convincing data examples offline. If you factorize U, you get embeddings that you can do pretty things with. So this is from a task of a choice problem of one of these things is not like the other, this triplet choice task that appeared in an HComp paper. And you get these, people are asked like, which of these 3 photos is most dissimilar? And if you learn this choice model, context dependent utility model on this data, you get sort of that all the mountain photos clumped together and sort of like the things that embedders like to see. I'm happy to talk about how you can interpret this as sort of a representation learning problem, or you can interpret representation learning problems as choice problems is probably the more accurate statement. Okay, so I do want to get to, I have like 5 minutes left, 8, 4, 6, 4, 5. I want to get to talking about ranking as choice. So what I talked about so far is just making choices from sets. And a very attractive way to approach ranking problems, sort of you're ranking things 1, 2, 3, 4, 5, is to view ranking problems as repeated choices. So the probability of seeing a given permutation 1, 2, 3, 4, 5 is the product of sort of the indexing here is important, sort of like picking 1 from 1 to n, picking 2 from 2 to n, picking 3 from 3 to n. So you're essentially taking a permutation 1, 2, 3, 4, 5, and you're converting it to 1 from 1, 2, 3, 4, 5, 2 from 2, 3, 4, 5, 3 from 3, 4, 5, and 4 from 4, 5. So if you if you consider a permutation to just be that sequence of choices, you're now fitting a choice model to items chosen from sets, item from set, item from set. And this is the what's done in the Plackett-Luce choice model. It's a little bit different than the literature on Mallow's models or mixtures of. And so we have this paper at NeurIPS, which basically said, what if you replace the MNL with this context-based choice model? Do you get, what kind of distributions do you get over SN, over the space of permutations? So for those who haven't seen these types of figures, as I'm showing on the right, this is all the permutations of 4 items with 1, 2, 3, 4 at the top. And permutations are connected if they have a distance 1 in Kendall tau distance. So if they're just a permutation, if there's only one transposition of adjacent items that moves from one ranking to the other. And so you can ask yourself sort of like, oh, like most people think 1, 2, 3, 4 is the ranking, but then there's like a distribution like going down from there. And so in fact, what this model can do is that if you have distributions like the data on the left, which has sort of like several modes, sort of like 2 peaked, Plackett-Luce struggles with that because it assumes everything is due to an inherent utility. And so it tries to fit sort of like a single peak distribution. The Mallow's model has the same problem, but the model in this paper, which is about doing contextual choices and learning embeddings of how things interact, has no problem imagining the idea that there's sort of like multiple modes in this distribution on SN. And so this is all 3 of the right-hand sides are sort of like maximum likelihood estimates fit to the data on the left. And so the similar in the choice setting, we have expected risk bounds of sort of like how quickly the MLE converges in on the true parameters. And here's a point where I get to just like embarrass myself by saying I have an upper bound that, you know, it's 10 to the 7 over L. So if there's 10 items, you only need 10 to the 7 items to have like a bound on the expected risk. That's not that bad, right? And then there's that constant that I didn't even go into. But I get to show some days of the week I'm a theorist, some days of the week I'm a ruthless practitioner. During this talk, during this slide, I'm definitely a theorist. We did a lot of work trying to get that end of the 7 down. It's hard. And actually, in trying to get that end of the 7 down, I should also say there's a second eigenvalue that's hiding in here that you can bound absolutely, which is sort of what that end of the 7 goes in. And I should point out that also for those of you who are in the stats literature, we have tail bounds, not just expected risk. They're just longer to put on slides. But in order to try, we started with end of the 8 log, end of the 6th or something like that. And we were able to shave off like n log 6 or something like that by sharpening the analysis of some of the basic machinery, sharpening the analysis of MNL, sharpening the analysis of the standard Plackett-Luce. So end of the 7th is not without effort. It was end of the 8th, but we were hoping to get down to something like, we think it's like end of the 3 or something like that. I actually forget what we think. We had a whole debate. So that's this space of sort of like learning models on choices, choice systems, learning models on permutations that I think there's a lot of interesting things happening with. I'm going to skip the last thing, which was this hypothesis testing problem. Feel free to ask me about it. It's about you get to construct use cycle decompositions of a particular graph to sort of like show that it's a very high dimensional problem and therefore it's statistically hard. Choice systems are good things. I want to sort of like promote their study, and there's all these doors between different things now, like looking at choice as a Markov chain problem, doing this truncation work. Testing IA, turns out testing IA is really hard because it's a high dimensional problem in a word. And then here are some of the papers about that underlie this talk. There's sort of the Markov chain work at NeurIPS 2016, ICML 2019 paper on the choice modeling, the testing problem. I've also done some work applying choice models to networks that are fun. If you like networks, I like networks. I didn't really do any network analysis in this talk, but it's something that I do other days of the week. And then the ranking problem is the most recent work that was at NeurIPS this past December. Thank you.